Well, Terry, please tell us about some of the exciting work you are currently doing with NASA propulsion and rockets.
Well, we at Lockheed Martin are the prime contractor to NASA for the Orion multipurpose crew vehicle. So that's a very exciting project that we've been working with NASA for a number of years now. We also have some work going on with Marshall in the area of the development of a habitat tied to the Artemis and Gateway program. And probably the biggest new program that we've all heard about is we, Lockheed Martin, as part of a national team, are helping pursue a lunar lander as part of the Human Lander System program. So that's what's really got us busy here, most recently with NASA Marshall.
What inspired you to become a NASA engineer?
Well, a number of things. I'd have to first cite an uncle, Robert Hardy. Robert was actually an engineer here in Huntsville working the Apollo program in the 60s, and he just encouraged me to pursue science and math. That and the fact that I've always just been fascinated with smoke and fire. I just really liked seeing things tested and built and flown, and just those types of situations always kind of pointed me toward an engineering degree.
So for those students watching that are interested in engineering sciences or propulsionary sciences, what classes would you recommend they take in school?
I would really emphasize, of course, anything in the math and science area, because as you would expect, an engineering degree will really focus in those technical areas. The other thing I guess I would cite is to be looking for those opportunities to get on a team at your high school, middle school that's club related, whether that's FIRST Robotics, Green Power Team comes to mind. There's just a number of neat organizations that are focusing upon collaboration, because what we really learn once you get beyond the book work, it takes a team, a diverse team with different areas of strengths and being able to identify ideas and a way to improve a product.
Well, I see you've brought a miniature rocket engine here on the table. Could you tell us a little bit about it, and we'll get ready for launch?
Absolutely. We developed a little demonstration rocket tool here that's on the table in front of us that's been extremely useful in explaining to students some of the basic principles of rocketry and rocket engines. For any rocket to operate, there's generally three elements that are required in a rocket engine. There's the rocket fuel, and in this case, my fuel is a solid acrylic rod, which we actually have placed in the center of an injector and a nozzle. So our fuel is an acrylic rod. Our oxidizer, the second element, is gaseous oxygen. It's in this pressurized bottle. And the third element today is some sort of ignition source. I choose to use a simple electric wire today that we'll insert into the rocket so that it operates. So given the combination of that fuel, oxidizer, and an ignition source, you essentially put those items in a combustion chamber and you have a rocket. In our industry today, you have liquid rockets that generally that mix a liquid oxidizer with a liquid fuel. You have solid rockets for which the fuel and oxidizer are cast or mixed, much like you'd see on a 4th of July exhibit, or a solid rocket motor on the side of a rocket. Today, this is actually a hybrid rocket in that our fuel is solid, but our oxidizer is liquid, or in our case, gaseous. So what we're gonna do is I'm gonna take our igniter, which again is simply a piece of speaker wire that's run through an electrical circuit. We're going to insert it into the aft end of our combustion chamber. What I'd like to draw your attention to, and let me stand up, is we're going to open this valve, which will allow oxygen to flow into the combustion chamber, ignite the rocket, and of course you'll see the combustion process, because the thing that's unique today is our fuel and our combustion chamber are one and the same, and they're transparent, so you can see the combustion process at work. So what I'd like to draw your attention to is watch the ignition point in the aft end of the rocket, watch the combustion system fill with pressurized gas. You'll of course see the exhaust. What I'll also do is when it's operating, I will close this valve or operate this hand valve, and you'll hear the rocket throttle down, and you'll hear it almost shut off because we are deviating from its optimum operational range or mixture ratio. Let's give it a try and see what we can do. Like any rocket, let's have a countdown, okay? 5, 4, 3, 2, 1. Okay, I hope that you were able to see the mock diamonds in the exhaust as that gas expands supersonically through the nozzle. And then of course you can see the combustion process, and boy, are my ears ringing, because the mixture of an oxidizer with a fuel in the presence of an ignition system is indeed a rocket, and you've seen that demonstrated today.
So I know we worked and you did a demonstration with the hybrid rocket using both a liquid oxidizer and a solid fuel source. Is there an advantage to liquid fuel versus solid fuel?
Again, a great question. The benefit of a liquid propulsion system is controllability. You can throttle up, you can throttle down by adjusting the rate at which those propellants are delivered to the combustion chamber. Whereas in a solid rocket motor, you don't change that. If you see a rocket take off and it has strap-on boosters, those boosters burn for 120 seconds, let's say. For 2 minutes, it's going to burn and give you thrust assistance in exiting the gravity well, leaving the Earth, and then they're jettisoned away once they're burnt out. So the objective of a propulsion system dictates the type that you use. When we think back of the shuttle, the engines on the rear of the orbiter were liquid propulsion systems because they could be throttled. The large boosters outboard on the shuttle, and likewise the boosters that will be on the space launch system that we're going to fly next year along with the Orion capsule as we head on a flight test to the moon, those are solid rocket boosters. They will burn to completion. Once they're ignited, they don't throttle. It's tailored into the propellant. They jettison away, and then the liquid engines continue to propel you into space. So yes, the type of mission dictates the type of propulsion system that's used.
Where do you see the future of propulsion technology going in the next decade?
If you look at an advanced propulsion system, they're complex. And so one area that comes to mind, for instance, is additive manufacturing. The engine parts have often been in the thousands, and yet oftentimes what might be hundreds of parts can be reduced to a single part by virtue of 3D printing or additive manufacturing. And so that's a technology that started out with plastics and polymers and has now moved into exotic metals. And so we're able to build something like as complex as a rocket nozzle with cooling channels, but rather than each of those channels being an individual part, the entire assembly can be built as one part. So that's one area. Another would be green propellants. And then the third I would cite is nuclear thermal propulsion, using a reactor to heat liquid hydrogen, for instance, and expel it through the nozzle, creates a rocket that is an order of magnitude higher efficiency. I guess I would compare it to filling up your tank of gas here at the local gas station and driving all the way to California on a tank of gas. Imagine a big part of any rocket is, of course, the propellant tanks, but that's tied to how efficiently the engine consumes those propellants. Well, nuclear thermal essentially has an efficiency, a specific impulse is the rocket term, that's 4 times higher than your typical rocket. So nuclear thermal is a neat area that you see NASA and DoD doing some recent and continued research in.
That sounds like a bright future ahead of us in rocketry.
It's some neat work going on.